organising this wonderful event. Yeah, so I'm going to be talking about my experience with teaching with Lean, but about teaching in general, the challenges that there are. So I guess so not everyone, I guess, knows what, everyone here knows what Lean is, but the people in the internet maybe don't, so I'm going to just say what it is. So what Lean is, there's a number of different things to different people. So it's this project at Microsoft Research. There's a few versions that are out there. There's Lean 3, which is written in C++, and Lean 4, which is written in Lean. Lean 3 is an interactive theorem proof, and Lean 4 is a general purpose functional programming language. And it's got a few features. It's based on dependent type theory, in particular the calculus conducted constructions rather, and the propositions, the things that you prove, are types in this theory, and your proofs are terms in this theory. And it's its own metaprogramming language. And there's MathLib, which is a community-driven project aimed at formalizing maths in Lean. So that's what Lean is. And what about teaching in Lean? So there are lots of people teaching in Lean. I think we've already heard of. I can't list all the people who are teaching with Lean here, but there is a link to the CU using Lean webpage. I first encountered it through this logic and proof course at Carnegie Mellon. So that's mainly focused on term-based instead of tactic-based proof. And that was for a general audience, and it alternates between a few different modes of proof. And is this working? Can everyone hear this? There's handwritten proofs, Jensen diagrams, and Lean proofs. Then you may all have heard of the natural number game. That was designed by Kevin Buzzard and game engine by Drum Farm. And that's more tactic-based, and it's a game. Then there's Patrick Masseau, who's been using a controlled natural language. So the idea of that is to make the transfer of using Lean to handwritten proof easier. And that's quite important. I'll be talking about some of that later, the transfer. And it's based on convergence of sequences, and it's meant to be for students who already have an introduction to proof module. And then there's the mechanics of proof by Heather Macbeth, and Heather uses proof by calculation. I've been doing a few things, including a game style thing called Modern Mathematics with Lean. It's still in Lean 3 at the moment, so I'm working on moving it to Lean 4. So that's a little bit about so Lean and teaching with Lean. And what's the context for me? So before Lean, before this thing came along, I've been teaching this large module class, or whatever you want to call it, at the University of Exeter, about 260 students, mixed abilities. The students who are great at maths, they do fine, they don't need any extra help. So I'm looking at the kind of weaker end of the cohort, of this large cohort. How do we help that weaker end? I teach this introduction to pure maths module, and at Exeter, which is in the United Kingdom, we have this tradition of something called applied maths. So it's like maths, but it's not maths. But we have a lot of it in our UK universities. So at the University of Exeter, not everything we do is maths in the maths department. There's a lot of applied maths. So actually, the pure maths is crammed into a small module. So this small module in the first year, of course there's more in later years, but in the first year, they learn all of the stuff about logic, sets, functions, sequences, series, group theory, linear algebra, number theory, all in one module. So I've been teaching this module. And every year there are a significant minority of students who don't get proof at all. And in the UK, we're not allowed to just fail everyone. You're meant to pass as many students as you can. So this is a problem. And so what is the problem? So the most fundamental problem I think for these students is how they read mathematics. So they're going to write expressions that don't type check because they're making category mistakes. And why is this? They make these mistakes because they don't consider the meaning of any given expression. So to them, expressions are just symbols to act with. So I was thinking, how do I help these students? And I had a personal familiarity with the Haskell functional programming language, and I used it in outreach work with schools. And I thought, well, maybe this will help them stop making category mistakes. So I never got as far as actually using Haskell in my first year course, but I then came across in 2019 the Logic and Proof resource at Carnegie Mellon by Agalis and Van Doorn. And I thought, yeah, this is a brilliant resource. I adapted it, stole it, whatever you want to call it. I stole the ideas from that, and I used it in my own module. So started off with just proof, and in outreach work with schools, and then I built on that and did my own thing with it. And for most of us, I mean, you're all here, you've all enjoyed Lean, it's been fun, and Lean is clearly the answer. But what is the question? So we're going to be, because so it's easy to say, oh, Lean is excellent, I'm having fun, students will get how to do maths from doing Lean, but we have to understand why is it that students are struggling, and then I'll try to apply some theory with it. Okay, so this is what I'm going to do in the talk. There isn't actually going to be that much Lean in the talk, it's going to be more about what are the problems that students have, how can we help them with these problems. So I'm going to identify common student errors and challenges, put these challenges within some kind of pedagogical framework, try to understand why the students are struggling, discuss how I've used Lean in my teaching, and then I'm going to criticize my own use of Lean in relation to this framework and look at future developments. So for example, talking about teaching students and then just being baffled by what they're not getting, right? Because often the student has a problem and the solution to the problem is just apply the definition. And why is the student not just applying the definition? So we have to try to go into the mind of the student and see what's happening. So here are some of the kinds of errors we're going to be looking at. Errors in propositional logic, these category mistakes, using descriptions rather than definitions, what we'll call quantifier blindness, relying on examples rather than definitions, and poor engagement with feedback. So let's look at the first of those to begin with. So if you've taught undergraduates, you'll come across probably all of these errors, or at least some of them. So the first one is very common and probably makes sense. So that students think that P or Q means P or Q, but not both P and Q. That's not correct in maths, but it is correct in a lot of ordinary speech. So it's kind of understandable when students make that error. But then there are these other errors that may be more confusing. So the student will treat a statement and its converse as being the same. Or if you tell the student, oh, we have P implies Q, the student will think, well, that means we also have P. Maybe you've encountered this. I certainly have many times. And then what about negating an implication? So the student might think the negation of P implies Q is not P implies not Q. So why is it that the student makes this or has this belief? Well, I'm going to position this within this framework. There was David Toole, 2008, had this idea of so-called set befores and metaphors in his paper, The Transition to Formal Thinking in Mathematics. So what are set befores? These are the innate mental structures we're all supposed to have that are fundamental to learning. So there are three of them. There's pattern recognition, there's repetition of actions until they become automatic, and then using language to describe and refine the way we think about And certainly in the UK, you can get a very good mark in high school mathematics just by using those first two skills, the pattern recognition and repetition of actions until they become more. So maybe the student has to learn how to differentiate functions, or really expressions. I don't think students know what functions are. They learn how to differentiate expressions. And the way they do this is by recognizing, oh, if I see something that looks like x to the n, then I turn it into n times x to the n minus 1. So they've learned this. They've learned this rule. They know how to work with monomials, and they have the idea that if you have a sum of monomials, you can apply differentiation to each of the terms and sum up the resultant derivatives. And they also have these met before. So what is a met before? A met before current mental facility based on specific high experiences of the individual. And some of these met befores, when they come to university, are unhelpful. So the met before, in this case, would be I've learned how to differentiate, and differentiating means applying certain rules to certain classes of functions or expressions rather than having a definition. So how does that relate to the implication? Confusion regarding implication. The notes there. The notes are not here. Okay, I have to try to remember what I've written there. So, oh yeah. So let's look at the leading P follows from P implies Q. Oh no, I think it is in there. So we'll see how it goes. So here's a typical instance of how a student might incorrectly use implication. So we've got this question, which is to solve the equation 2x plus 3 equals 7 by x. It doesn't even say that, it's solve the equation. So the student might use the implication symbol as punctuation. So they write down one line, which is the symbol you're given. They do something to the side, and you get 2x equals 4. Okay, so you've got a 2. So what does a 2x mean here to the student? What does the implication mean? It just means, oh, here's something I have. I've got the 2x. And I think this is one of the things that can cause difficulties with lean as well when the students are using lean. Like, what does it mean to have something? So they see this equation 2x equals 4. 2x to them is something they have. It's not a proposition, it's an expression. You can have an expression. Or at least that's how it is to the student. And that's why when the student sees P implies Q, what it means to them is that we have P and we get Q from P. So that's what P implies Q means. So that's where that error comes from. How can we avoid this error? Well, by being clear about what the context is. The student can help not to make, or we can help the student not to make this mistake, and that's where lean can be helpful, because you can see the goal state shown in the context. You're proving something. Okay, so why do students make this kind of mistake? Well, there's a book, I've just been reading a book on grammar called The Cambridge Grammar of the English Language. And in this book, Holston and Cullum, 2002, have this notion of conversational implicature. These are the things that follow, the meaning that follows from the conventions of conversations, and not truth conditional. When we use language, we don't, well, most people, when they use language, do not use it in a truth conditional way. Things that are meant that don't follow in a truth conditional manner. So if you just an example, if you tell a student, if you submit your work late, it will be capped at 40%. And let's suppose the student submits the work on time, and you still cap them at 40%. Now, the student says to you, wait a minute, that's not what you said. You said if I submit my work late, you cap at 40%, and you cap my work at 40%, even though I submitted on time. So they're treating the conditional as a biconditional. That's what it means to them. It's not an implication.
It would still be mean to do that.
It would still be mean to do that, but it would teach them something about it. Or, yeah, or whoever writes the university regulations. Right, so, okay, so then we've got the category mistakes. So this idea of category mistake was introduced by philosopher Gilbert Ryle, and he did it to argue against Cartesian dualism. He thought it was a kind of category error, so category mistake to have this mind or the duality. But his famous example is you've got a visitor to the University of Oxford, and they're being shown around. You see lots of buildings. You've got the colleges of the university, you've got the library, the administrative buildings, etc. And the visitor says, okay, I've seen one of these buildings, but where is the university? So they make the category mistake of thinking that the university, which of course is just the collection of those objects and the relationship between those objects, is an object in the same category as those objects. And it's not unusual for students to make category mistakes. They do it all the time. So here's an example of a category mistake a student might make. Getting confused between set membership and set inclusion. So they're going to prove that the empty set belongs to the empty set as an element of the empty set. The argument would be something like, nothing belongs to the empty set, and the empty set is nothing. So the empty set belongs to the empty set. So this one, the next one is an actual genuine error that a student has made. So here's a task. You've got a set defined like this, a set of triples x, y, z in R cubed such that x plus y z is 0. And the question is it a subspace of R cubed? So the student knows that to prove something is a subspace, you've got to prove certain properties, 3 properties. So let's prove one of those properties. So they know that they have to prove that if lambda belongs to f, they're not saying what f is here, they just learn. And u belongs to u, then they need to prove that lambda u belongs to big U. Right? So they look at lambda u. Now, what is u? U is an element of the set, big U. But what is big U? Well, we've got this thing with x plus yz. Yeah, so it's lambda times x plus yz. So they make the category mistake of confusing the vector with its components. But why have they made that mistake? Well, it's because set comprehension is not an obvious thing. I thought this was obvious. It's not obvious. I don't know if you taught undergraduates. It's not at all clear how to work with set comprehensions. Why is it not clear? I think it's because understanding that there are things called predicates is not an obvious thing. Right? So expressions are fine. X plus yz, that's a fine thing that they understand. Predicates are fine. I think, and this is the same issue we see many times. Functions, I don't think students do have a notion of function from school, or they think of functions as expressions. A function is an expression. And so there is a confusion between predicates and ordinary functions or expressions, or between propositions and terms of other types. So let's take a simple proof by induction. So the student has to prove basic high school formula, and maybe they've been taught, or they have been taught some kind of formal way of doing this. I say, we have to introduce some kind of predicate, and I'm going to prove this predicate holds. And they know that to prove the base case is to prove that P of naught holds. But not having a notion of predicate, they're always trying to turn it into an ordinary expression. So then, instead of having a predicate, they replace the predicate with this expression. So P of n is a half n plus 1. So P of naught must be a half n naught times naught plus 1. And that's true. Exactly what that means for that to be true is unclear. And then they assume something and so forth. Right? So they're following a kind of pattern. this is maybe one of those two skills we mentioned before, the set-befores and met-befores, kind of working with patterns, but without understanding what's happening. Okay. Is another example using descriptions rather than definitions. What does it mean for a sequence AN of real numbers to converge to a real number X? So there are two possible different answers that I have seen in exam script. So one student writes, it means AN tends to A as n tends to infinity. Another student might write, it means AN gets closer and closer to A but never reaches A. And of course, that's not the answer I was looking for. But there's a reason why the students are writing this. Right? It's not like students are idiots. There is a reason why these mistakes occur because of the mental conditioning that we've all been through. So I'm going to put this in the framework of something called stipulative and descriptive definitions. I mean, I've said C. So this is from the Stanford. It's philosophy. I mean, these are old notions. I think Frege talked about this. So what is a stipulative definition? Well, let's look at the definition I wanted them to give for the convergence. I wanted them to give the epsilon n definition of convergence. But of course, mathematicians talked about convergence way before Cauchy came along. So there was this notion of what it meant for a sequence to converge, and of course. That's not, the epsilon n definition is not the only definition. Of course, when students look at topological spaces or filters, maybe at some point they'll come across different notions. So a stipulative definition is a definition that imparts a meaning to the defined term and involves no commitment that the assigned meaning agrees with any prior use of the term. Right, so the student might have some idea in their head of convergence, but when we define convergence using the epsilon n definition, we're saying, well, don't think about whatever idea you might have had in your head, it's this one now. There might be pathological examples, of course. Now, though as working mathematicians, like if someone came up to you with a definition of convergence that didn't correspond to your intuition, you would say, well, that's not the right definition. Of course, you can't argue, in some sense, you can't argue with the stipulative definition. At the same time, you want it to correspond to the notion you already have in your head. But the difference is, with the working mathematician says, okay, this looks like a good stipulative definition, it corresponds to my descriptive idea in my head, but I don't work with the descriptive definition, I work with the stipulative definition. So it's not that one is good and the other is bad, you need both the stipulative and the descriptive definition. If you just have the stipulative definition and no concept in your head, it would just be formal and unpleasant. Or maybe it would be pleasant, but it wouldn't be understandable. But the high school student is only familiar with the descriptive definition. They only have this vague notion in their minds of what it is for something to converge. So when they see a stipulative definition given in a lecture theatre of what it means for a sequence to converge, to them it is just another kind of description of convergence. It's not a stipulation of the definition. Maybe it's just a description that isn't very helpful to them. It's like, I don't really understand what these epsilons and n's. I know what it means for something to converge. So, how can, of course, I mean, probably obvious now how lean comes with this, because with lean, you can't give it a description. I have seen actually students trying to type in English statements to lean. It doesn't work. I don't know why they think they can do this. But yeah, if you type English into lean, it doesn't work. But lean only deals with stipulative definitions, so hopefully that will, working with lean will help students to work with stipulative definitions. But the danger, of course, is that students will then ignore their descriptive definition, especially if they're doing interactive theorem proving. They've got this goal state. Maybe just focus on what the goal is, the current goal is, without having an overall idea in mind. So that's the danger. Okay, so Another thing I called quantifier blindness or scope problems. So this is another language issue. So here's an example. Is it an actual question? I don't know. All right, well, this could be an exam question. I don't know if it will or not. Probably. So prove that there exists a set A such that a set B, A is a subset of B, and here is the student's answer. Well, we'll let A equal B, yeah? If we let A equals B, then when we write A as a subset of B, that's just the same thing as B as a subset of B. We know that's true, so there we are. That's the proof. Okay. So why has the student made this mistake here? Because they're focusing on just the bit at the end, the A is a subset of B. So there's all of this stuff before the quantifiers, and it's like the order of the quantifiers doesn't matter. You can just put them in any order. The fact that there's some scope of the quantifier also doesn't matter. So the scope of the variable B only really extends to the universally quantified part of the statement. It doesn't extend beyond that, but the student doesn't see this at all. So in Lean, you can't, of course, it's just going to hate you if you try to write something like this. It will give you lots of error messages, so the student cannot make that error. Okay, so let's see. Oh, okay. Right, so let's try to put this again within some kind of pedagogical framework. So it's from the same paper of David Tall, Three Worlds of Mathematics. So he sees mathematics as being, or learning mathematics as among these three worlds. There's the conceptual embodied world. So it could be, yeah, I think up to when I was a child, I was hearing about this big issue that people had about non-Euclidean geometries, and I didn't quite get what the problem was. And I guess the problem was that at the time, people saw geometry as like a descriptive thing, like Euclidean geometry to describe the way the world actually was. So, whatever it is, that's meant to be something real that we're describing physical. And we all kind of start off with this conceptual embodied understanding of mathematics. And maybe in terms of sets, they might have an idea of set as being like a bunch of stuff, a bag with things in it. And then there's the proceptual symbolic world. So procept is just a combination of process and concept. So the student learns processes for dealing with things, maybe arithmetic, or with sets it might be, I don't know, set operations kind of thing. And they've got some kind of concept of it. But then the next level is the axiomatic formal world. So, and again, the first two worlds are sufficient for high school mathematics. And they move to the axiomatic formal world, and if they're just working with the first two worlds, it doesn't work because they need to have language skills. They need to think of this as statements and syntax and semantics. So we've got relying on examples. So here's sorry, I don't know how ethical this is. Yeah, so this is a real question, a real student asked me this question. So, so this is from an exam question. You've got some linear map, phi. Oh, there's a typo there, obviously.
Or maybe the student was right.
Yeah, I think the student was right, yeah. Yeah, I guess that would be 2 times phi of x. Yeah, so you've got some linear map phi and theta. Theta is theta of x is 2 times phi of x. Proves that theta is a linear map. So it says, how do I do this question? I haven't seen anything like it in the lectures. And the instructor says, what is the definition of a linear map? And the student says, I don't know. Now, we might want to look, why didn't the student think to ask what is the definition before trying the problem? But that's simply because they don't have to work with definitions at school. It's not important. So this is again going on to going back to the these first two worlds of mathematics. Okay, so then the last thing I wanted to talk about in this section was effective engagement with feedback. I don't know, this is a term, all these, so I don't know, feedback wasn't a term that existed when I was at university, but now it's a term, probably because there's something called the National Student Survey, and all the students are asked, how did you get lots of feedback or something like this? So feedback is some notion. I think what it means is the student does some work, you mark their work, and they're meant to improve based on how you mark them and what comments they got in their marking. Okay, but certainly at my institution, there's a very poor engagement with the feedback. And why? Yeah, so the students often just ignore the feedback, they get back their marked work and file it away, don't look at the feedback. But why is that? Again, there's a reason that the blame isn't on the student, the blame is on the system. So one reason is that the student hands in their work, takes maybe a week or something, it gets marked, it gets returned to them, and by that time in the lecture course they've moved on to something else, they've forgotten what exactly they wrote. The marks and the comments on the script mean nothing to them. If they didn't know how to do the problem in the first place, often the comments don't help them because it's in this formal language that they weren't expecting anyway. And they also don't know, well, if I change my work, will it still be correct? I don't know. I'm going to do some new piece of work and it might still be incorrect. So there's no kind of feedback loop or positive feedback with no way of making an incremental improvement. But of course there is with Lean. You get immediate feedback if your proof is incorrect. You got immediate feedback, and incremental improvement is possible, but one might be syntax errors kill everything, which they don't inherent in maths. If you put a full stop in the wrong place or misspell something, it doesn't matter, the instructor knows what you mean. Lean doesn't. The error messages aren't very helpful. They talk about some kind of type of theoretic stuff that the students won't understand. It's not going to help them. And also, as is the case with any computer language, the error might not be in the place where the message is pointing to. It might be a few lines up or a few lines down, and the student won't necessarily. Okay, so I'll come back to this issue later on. Okay, so these are all the challenges, difficulties. What about? Is there anything we can do with Lean? Okay, so I call this the Lean advantage. So there's proof with context. So one of the biggest wins for me from having taught since 2019 with these students is that student vocabulary has changed now, not just in the module I teach, but in other modules. So they start talking about goals, targets, context, and hypotheses. Now, just using terms doesn't mean anything, but the fact that they're using these terms means that they're aware that there is something in a proof. When you're writing a proof, it's not just a bunch of meaningless symbols. Something is like happening. Certainly is if you're doing tactical proofs. So what's one of the other wins? Well, another win is this in terms of data tool and set before the set before of repetition. So it's very important in order for the student to understand the stipulative definitions help you do mathematics, to actually have lots and lots of practice working with stipulative definitions. So with Lean, that's the only kind of definition you can work with. You can't work with descriptive definitions. So that's very useful. Likewise, they will undo, hopefully, their unhelpful met-befores of logic. So this idea that if you have P implies Q, then you have P. Hopefully, the student will see in the tactic state that if you have P implies Q, you don't have P. If the student understands it, then they won't make that error. And then the category mistakes in general become type errors in Lean. So the student can't make a category mistake, or they can, but they'll see that they made a mistake. Likewise, working explicitly with quantifiers means that they won't make problems of scope. So then this one, the last one, it's I don't know whether it's an advantage or a disadvantage. So I've written that reasoning must be explicit. So every line you write must be justified. Now, I don't know, is that an advantage or a disadvantage? Now, of course, in ordinary handwritten maths, people don't write down reasoning for everything they write. Now, there's a lot of proof automation in Lean that you can have simple errors. But this is where the instructor has to be judicious in how they use Lean. You shouldn't be requiring the students to do lots of things that they wouldn't do in a handwritten proof. So if the proof involves things that, I don't know, involve, if you have to prove that 2 is a positive number or something like that, that should somehow, perhaps, as an instructor, you should kind of build that in as a simple one, so you're not having to prove it. I'll discuss other ways of working. Okay, so what about, yeah, so my own practice with Lean. So what I did when I started off with Lean was I made my own online lecture notes. I guess similar in style to the logic and proof notes that combined Lean with mathematics. I also so this was during the lockdown. I think it actually really helped it work very well during the lockdown because each student would have their own computer. There was a cloud computing platform called CoCalc. There is one, I think, and students could do their work on CoCalc. And then I would have online workshops. So I would run some of the workshops. I would have also in the second year senior undergraduates running the workshops. I think that's really useful because if students talk to their peers, it's a lot more helpful than necessarily speaking to a lecturer. I use Discord as well for large scale conversations. It was actually a little harder when they all came back into in-person teaching.
So can I ask, the students really were doing Lean proofs here on their own?
Yes, yeah.
I see, okay.
So then the next phase, I guess the last couple of years or so, I think it was last year maybe. So I have my lecture notes that alternate between straight maths chapters and Lean chapters. And one of the reasons I did this was because we found out very early on that if you try to teach maths in Lean, that's very challenging for the students because they have to learn Lean and maths at the same time. So you have to teach them maths first. So I've got this online game, the Modern Maths with Lean game, using the same engine as the natural number game. I also created some induction activities for the MIU game. So I know that everyone's read Gödel-Escher Bark. So in Gödel-Escher Bark, Douglas Hofstadter came up with this very small formal language which has 3 symbols, M, I, and U, and a few rules. And then you're meant to ask is N, U a derivable string in this language. So I formalized that into Lean. I think that's quite good because there are no met-befores for the students. They don't have any prior incorrect conceptions of how you can work within this system. So that allows them to train their deductive processes without things getting in the way. And I've also done assessment of the lean. So I did that for the first time last year, where the students actually submitted their work. So I think Matthew Ballard has been doing this as well, using GitHub Classroom and GitHub Code Spaces. I'll talk maybe a bit more about that later. And that was supported via computer labs. So I'll talk a bit now about that assessment. So I think, so if any of you have used GitHub Classroom, the way it works is that you have your template repository, and then you publish it in your classroom, and the students will get their own copy of that repository. And they can also, if they're using GitHub Code Spaces, work with that via a GitHub Code Spaces VS Code container. So the way they submit their work is just by pushing a commit on the GitHub Code Spaces, and then it's work, then it's auto graded, and the student either gets a perfect score or gets 0. There's no in between. So one of the difficulties is that it's quite hard to reconcile the auto-graded marks with your university's mark system, so you might have to write some script to do that if you're wanting to do something like this yourself. I mean, if it's just a small number of students, you can probably do it manually. If you've got 260 students, you have to write a script to do it. The other thing I found, of course, if a student hasn't used Git or GitHub before, then they need to be able to learn how to do that. And in particular, they might think, oh, I've submitted my work, either because there's no error messages or because they've made a commit, but they haven't pushed the commit. So, yeah, so they need training how to make sure they know they've submitted. I made a practice assessment. I thought that was a good idea. But not all of the students did engage with the practice assessment, so you just want to make sure they all engage with the practice assessment. And then the students also might, like I said, because they might think that they've passed, you should email them the marks or something like that as well to make sure that they know they've submitted. One of the issues, as I said, was it's 0 or a perfect score. So what I do is that if the student submits something that doesn't quite work, then you can look at it manually and give them some kind of half mark. It would be better perhaps if there were more people on the module so that nobody could, the marking could be shared and maybe we'll do the auto marking. Plagiarism is easy. I mean, of course, plagiarism is often easy, but it's even easier with this kind of thing. I mean, if the student really knows what they're doing, they don't even need to write a correct answer. They can just change the auto grading script, because the auto grading script is part of the repository. Maybe I should be saying this. Cut that out. Yeah, GitHub Classrooms is not designed in a very clever way. Really easy to cheat on it. But also, since they all have the same assessment, they can copy from each other. And I'm not sure if that's easy to do in GitHub Classroom, and also how do you ensure that everyone has a different proof to do? I'm not sure how easy that would be, and would it be fair? So some proofs might be more difficult than that. Okay, so some reflections on the process. So as I said, a lot of the resources were on this web-based game, and WebAssembly, which we were just talking about the last session, I found to be really slow. Maybe in Lean 4 it's quicker, but
it doesn't exist.
Okay, yeah, but with Lean 3 it's like really slow, especially if you've got anything of any degree of complication. I think maybe for simple proofs, yeah, it's fine if you just write proofs of the problems in logic. It's not so hard. If you're proving anything slightly more complicated, it'd be incredibly slow. So then you're working with a non-interactive theorem prover. And what was the point of that? But also, I don't want to assume that every student can install Lean on a super fast machine that they have. Right? So we wouldn't be egalitarian. So that's why I think cloud computing is the way to go, using something like GitHub code spaces or Gitpod or something like that. Okay, so some other thoughts. I think it's useful to use gapped proofs. I kind of mentioned this earlier. So that is, you do the messy bits for the students. So maybe here's a proof. So this is, so in my model, one of the things was to show that there is a real number whose square is 2. One of the things I wanted the students to be able to do. So one of the steps in doing that is this to prove that this set of non-negative real numbers whose square is less than 2 has a subproblem. So just kind of start off by giving them some stuff. So these are some of the things that are not obvious to the student that they should be doing. And even if it is obvious, it's maybe not obvious how to do it in Lean. Like how do you show that a set that has an element is non-empty? I mean, that's not something you think that requires proof, but it does require proof. So you could sort of put some of those things in that are getting in the way in there. And either you could do it as a gap proof like this, or you could give them limits. Okay, so here's another thing. So coercions, they seem nasty, and perhaps they seem nasty because most of us were trained on set theory. And in set theory, yeah, it is nasty. I mean, you shouldn't need a coercion at all in set theory there. But I don't think set theory is natural at all. How many students have you had who say that 5 is not a complex number? Many students will say this. And because I think actually it's much more natural to think type theoretically. So it isn't, is it? No, it's not a natural number. Certainly the natural number 5 is not a complex number. So yeah, I don't know. So that's another thought. What about, okay, so probably one of the biggest issues is error messages. The code doesn't work, the student doesn't know why it doesn't work, and they're sad and they give up. And you might think, well, okay, well, they just need to kind of debug the code. But debugging code is not something that people are taught to do at school. So it's something that needs to be taught, explicitly taught. How do you deal with error messages? So you need to get the students to make errors and then tell them how to deal with these errors. And why is assessment important? There's something called, I don't know, the theory in education, constructive alignment or something like that. So the idea is you've got to align your assessment with the teaching that you're doing. Otherwise, the students aren't interested in it. Okay, and then we've got another question about tactic mode versus tactic mode proof versus a term start proof. So I was thinking, when I started off doing Lean, I was thinking, students would really like Lean because it's calculation, which they're good at. But then I realised actually it's not calculation, because certainly if you're doing a term style proof, you're just writing a term, and what happens is that Lean checks the type of the term. But so the calculation or the computation is writing a tactic mode proof. But the problem with a tactic mode proof, like a computer program, is that on the whole they're not meant to be read by humans. So if you look at a tactic mode Lean proof, it's hard to reconstruct in your mind the goal state. So if you are using tactic mode proofs, you need to introduce a style of proof writing which is very verbose. It's the opposite of code law. So you need to. I've just used a simple tactic I called given, which given doesn't do anything. It just says we've got a hypothesis H2 in the context. So the case statement with YH2. It's not clear when you read that exactly what's happening. This statement changes the context. That's not clear unless you know how the basis statement works. And that's why you need to pull in extra things. So use these kind of statements as much as possible, but make explicit what's happening implicitly in the goal statement. Okay, so yeah, so what's happening at the moment, or what am I developing in terms of my practice? So I've got firstly I've been writing this book, and it's more, it's maths with lean, not maths in lean. There's maths and there's lean, and you could read just the maths chapters if you wanted to, and you'd still get something out of it. But by writing this book with a lean hat on, it's kind of made me focus on a lot of the things that we take for granted, that we think do know, all the things that I was talking about before, these metaphors that are not helpful, the three worlds of mathematics. So students parsing expressions is not, it's not an easy thing, or at least it's not a natural thing. Students learn, I don't know, is it called bid maths or odd maths or something in school, the pretty much called something else entirely. So the order of precedence of operators. Is there an acronym for that? Yeah. Okay, maybe it's just so obvious, but okay. But Podmas? Bondas? Oh, maybe, yeah, Bondas, yeah. One of these things, Bondas. Yeah, but there is an order of precedence is drilled into the students. Actually, I've seen students make errors with this, even at university, with ordinary arithmetic expressions. But the fact that there is some kind of semantics to what we're writing when we write out a mathematical sentence, I think that's important to teach. It's crucial for lean, but it's also just important in general. And I go into definitions, types, functions, and various other things, and it alternates between straight maths and lean. And then this teaching how to deal with feedback is crucial. So, I think that's most of the things I wanted to say. So I'm going to just wrap up now. So what have we seen then in terms of lean and teaching? Well, I think there's a lot of potential in lean to correct some of the misconceptions that are natural to make and to develop proof skills. But you shouldn't just use lean. Probably I did this to start with. I probably use lean because this is really fun. This is so exciting, and it's going to work and everyone will understand. But you have to have a good understanding of the thought processes that are going on with the student. Why are they making these errors? And design your materials so that they address those particular issues and errors. Yeah, so I think that's basically all I have to say. Thanks for listening.
Do you have data how your students improve?
Yes, I noticed some improvement over the lockdown. I don't have the data here, but then that could also be due to the fact that all of the examinations were online. And then after the lockdown ended, students across the board did worse than everything because they had not been having their regular schooling. So we're in this state where it's very hard to draw any conclusions, except for talking to particular students who would then say, oh yeah, this has really helped me understand proof. So it's more qualitative rather than quantitative data. Yes?
What if instead of having a combined lean and math course, you had first a short course in lean, and then have them learn the math using the library? Do you think that would work out?
Yeah, that could work too.
Because I mean, libraries way more difficult than a textbook, so for them it would be easier to go and look at the details.
Can you maybe repeat the questions for the people who are following online because they won't hear what the
Yes,
question is?
okay. So the first question was, did I have any data about how the students were progressing? And then the second question was, what about having a short course just on lean first, and then do the mathematics? And I said, yeah, that would work. Any other questions?
Can you please go to functions and expressions slide?
Yeah.
And explain again what was the answer?
Yeah, I guess there were a few cases where, well, perhaps it's even clearer if I look at the previous slide. Where is it clear? Okay, it's not clear. Oh, perhaps it is clear here. So here, there is a function here, but it's a predicate. There's a predicate, x plus y z equals 0. And since to the students at school, functions are really just kind of symbolic expressions, right? So the students will talk about the function x squared, for example. So that's a function. Therefore, a predicate, whatever it is, must also be an expression. So rather than thinking of x plus y z equals 0 as a mathematical object, which doesn't make sense, how can that be an object? They look at the thing that they know is a mathematical object, the x plus y z, and they just use that. Okay. Another question? Yeah.
How do you assess dealing with error messages?
What you do is you would give them a bit of code with an error in it, and then the question, then can they fix the error? How do you? Oh, sorry. Repeating the question. I'm sorry. There was a previous question too, so I'll repeat both questions. The first question was, how do you assess dealing with error messages? Was the most recent question, and the answer was you would give them some code with an error message and ask them to correct it. And the previous question was, what's going on with functions as expressions? Any other questions?